Welcome back, welcome back. Last question we discussed the Dirac delta function, its definitions, and how to apply it to a couple of the integral expressions and how to manipulate the forms to get us a result and where the result is actually valid, things about the, being in a range, things of that nature from last question. But for this question, what we're asked to do is to prove or demonstrate an equivalence of two expressions in A and B using the definition with the integrals as stated here, which says that two expressions involving delta functions which live in integrals are said to be equal if we have the integral f of x times d1 of x, and this expression holds the delta function, is equal to the integral of f of x d2, which this has another delta function, f of x, or delta x times dx. And why is this the case of equivalence? Well, recall that the delta term is defined within an integral to have a finite area. So if both of these modulations, or however we algebraically manipulate the delta terms, equal the same finite area, then we can call them equivalent. Again, we have to be careful with what f of x is, and this is said to be true for every ordinary function f of x. That's the kind of functions we've seen in our algebra classes and that we've worked with. There are some specialty functions where this will fail, but we're not in an analysis class, so we're not going to have to worry about that. But for what we wish to show, in part A, we wish to show that delta of c times x is equal to 1 over the magnitude of c times the delta function at x, where c is a real number. So this is a scaling law per se. A couple books write it out a little different, but these are still properties nonetheless. And then in part B, theta of x is said to be the step function, as defined by 1 for x greater than 0 and 0 for x less than 0. And on certain of rare occasions, what they will do is take the average of the 2 points at x equals 0. As you see here, we're strict inequalities, not equal to's. So some texts will put that theta of x is equal to 1/2, or right in the middle at x equals 0. Not so much of a worry here yet, but good to know. And what we wish to show is that the derivative of this step function is equal to the Dirac delta. So we have our work cut out for us. We know what we need to do with the equivalence, and we know we're going to have a bunch of integral functions. So let's dive in. So in part A, we wanted to show that we had an equivalence of the delta with a modulated argument, i.e. c of x. And since this is an integral equation, we may as well use a substitution like we've seen 1,000 times before. In this case, I'm going to let u equal cx. So if we solve this for x, we get u over c equals x, no big deal. Take the derivative, we get du by dx equals c, so dx is equal to du. And of course, we could substitute this into the integral and move forward with it. However, we have to take into account the fact that c was not stated as positive or negative, so we have to set up conditionals, which we see in green and blue, for the case where c is less than 0, and for the case of c greater than 0. Why is this the case? Well, if we go back to our substitution variable here, it's a function of x. So if we plug the bounds in of plus infinity, minus infinity into the substitution variable, we see that we get c plus or minus infinity, but if c is less than 0, that's negative, so you get a double, so you have to multiply the whole thing by negative. And so these signs flip. So instead of plus minus, I end up with minus plus. If we're greater than c, great, no worries there. But you see here in the when we plug in the substitution, the bounds are going to matter in the entirety of this support proof that we have. So just be mindful, we have two cases to deal with, and we'll color code them with green and blue accordingly. So be on the lookout for that. All right, so now that we have the, now that we know that we're going to have case systems to set up, let's go ahead and simplify the use of which we just do, which we bring out the c's as constants. We plug in the coefficients, the limits that we have with each case. Notice that I have a plus and a minus here just to indicate that those are different. And we're left with the normal used subintegral. No big deal. What we can do is use our property of integrals where if I want to switch the limits of integration, I can do that at the cost of a minus sign. So you see the reds here, we switched it with the cost of a minus sign in order to switch the order. And now we're in pretty good standing. The next step is going to look kind of weird if you're not familiar with just how to join together two sets of things acting like this, or two conditions. But notice here that with the negative sign now introduced, we're going to be able to simplify this down pretty quickly. And we'll show you how next step. Alrighty. So before we can finish simplifying this thing, we have to take a note of the fact that the integrals themselves need to be evaluated with the sifting property, or evaluate the function f of u over c at x equals 0, because that's what the Dirac delta tells us to do. And we see that 0 over c gives us a function value of 0. So we know that so we end up with f of 0 in both of those integral terms. But what we're still left with is the fact that we have a negative 1 over c for the green and a 1 over c for the blue. But let's take a quick note here that c is less than 0. So if that's the case, if we put in any value of c here, we get a double negative situation, and so the signs cancel out. What this allows us to do, or rather to say, is that these functions are the same magnitude, and the magnitude is the 1 over c factor, and that's all because of the signs canceling, the double negative. Wonderful, wonderful, wonderful. And so we can write this expression here. What we're going to do now is restate the integral expression that we were trying to show, which was f of x delta cx, cx times dx, and that's equal to the result we just found up here. What I want to highlight in this orange, though, is that this f of 0 is equal to the integral of f of x delta x dx, and we just have a constant of 1 over c there. And why do we want to push this back in and color code the orange there? Well, let's go back to how we were supposed to state the equivalences. It was two integrals equaling one another, where we had d1 and d2, and if so long as they were the same, then the d1 and d2 were equal. So what does this mean? Well, here d1 is our delta c of x term. This is our integral 1 on the left-hand side from the definition on the first page. And then d2 here is equal to, once we shove this constant back in after resubbing in the orange term for the integral expression as a whole, what we see is that c, 1 over magnitude c, and the delta come together, and that forms our d2. So since these are both equivalent expressions, these delta term factors must be equal, and that's what we see in the purple box, and we have successfully proven what we wanted to with this property. So now that you see how to set up and verify with the two integral statements of equivalence, now we can kind of maneuver our way through the next part of this, and remember to bring your calculus game with it. It'll come in handy. Alrighty, so on to part B now. We know that we are going to have another integral equation, integral expression, and in this time, what we want to do is, we have to keep our f of x right here. So we define our d1 term as d theta over dx. And here is where I said, remember to bring your calculus, because it will be used here insofar as the fact that we need to use integration by parts. And if you don't remember what that was, this integral v to u is equal to uv minus integral v to u. Cool, cool. So what we need to do is, since we have a derivative here and a function, or a product in the integrand, let's go ahead and integrate this out using integration by parts with these substitutions. If you're unfamiliar with it, we can chat it up later, but here's how to set it up. Define your u, define your dv, here's your du and v, and so let's substitute it in, and the form is written here. But beware that if you have a definite integral, you need to evaluate the UV term at the boundaries too, and keep the boundaries or the limits on the integral as you go to the VDU term. So that's what we have here. And you might notice that I color-coded a bunch of blue and green for the positive and negative infinities. And this is because we need to remember the definition of the step function that was given to us, which was 1 for x greater than 0 and 0 for x less than 0. So the signage of these do matter. So we'll do blue for positive and green for the negative, and the step function attains different values for that for those directions, and rather those domains, not directions. So what we want to do, evaluate this as you would normally. So f positive infinity, theta positive infinity minus f negative, theta negative, cool. But what we want to do for this integral is split them up into two separate integrals with the positive domain and the negative domain. And we'll see here that this leads to a lovely, lovely cancellation due to our zeros. So anytime we have zeros, that makes life easy and we wish to use them. So let's see how that's done. Awesome, awesome. Coming down the home stretch now, we see that if we substitute in the values for the step function within those given domains, positive goes to 1, the negative goes to 0. So we have a 0 here in the integral expression and a 1 here in the integral expression. Wonderful! Now we don't have to use integration by parts again on the theta function and the derivative of the x. Cool, we like that, easy. Let the simplification run through. We get a 0 from here that goes here, and we're just left with f of positive infinity. And this integral expression goes to 0, which we see here. And we're still just left with this simple integral of a derivative, which of course we know we can use the fundamental theorem. And that's just f of x evaluated at the bounds. So once we do that, you see we get f of infinity minus f of infinity, which is just, or rather, we have to distribute this minus sign into the evaluation brackets here. So we get a negative on the f infinity and a double negative on the f0, which goes to positive, which is what we see in the next line. The infinities cancel, which they should have, of course. That would make no sense to have it without it. And so we see that this integral expression leads us back to f of 0, which of course we know is our integral of the delta function at 0 of f of x. So this is awesome, and if we go back to the integral expression of equivalence, we see here that our d1 was equal to d theta dx, and our d2 was equal to the delta term by itself. So by the equivalence statement that was given to us, we know that the derivative with respect to x of theta, the step function, is equal to the Dirac delta. That is freaking cool, and we will definitely see this in action, I want to say fairly soon. But also let's take a note to kind of look at this thing intrinsically or geometrically. What we know is that this kind of makes sense because the theta function is equal to a constant except for at 0. So if it's a constant except for at 0, we have a 0 derivative, the derivative of a constant is 0, and so what we can say is that since we blow up at 0, we go to infinity there because we do a jump discontinuity, and so it makes sense. We have infinity at 0, and we have 0 everywhere else, so this kind of works together. I know for a fact this is used all throughout signal analysis. Let's also take a second to note that the theta function is often referred to as the Heaviside step function. So there's a lot of different names for the same concept. Be aware, this is not a new property. It's been around for quite a while, but it's still useful nonetheless. Thank you for watching, and as always, until next time, happy learning.